Hey, I'm Blake Ludlow.
I'm Sam Cavagnaro.
I'm Robert Mayo.
And I'm Josh Tilley.
And we are the Trustworthy.
Our experience with the design cycle. First, we had to define the problem. We had to create a collapsible bridge that was able to fit into a cubic foot. It had to span 4 feet and be self-supported. It had to hold at least 60 pounds while weighing less than 8 pounds itself. We had to assemble it in a minute and disassemble it in a reasonable amount of time. We had to spend less than $40 on the bridge, and during the final test of the bridge, it could only deflect 25 degrees. The brainstorming process. At first, we didn't know the best material to use, and after some research, we found out that the cheapest and lightest of some common materials would probably be wood. The next step was figuring out a good shape, and after some more research, we found out that an arch would probably be the best. Another thing we looked into was running a string through the bridge to make it stronger, and this was a design we implemented into our final project.
Okay, so our initial design plan was to use pieces of wood that were less than a foot long and to drill a hole through each of them and then run a rope between them. The rope served the purpose of keeping the bridge organized for assembly, tensioning the bridge into shape to create an arch that we designed to bear the load, and just keeping everything organized in general. As you can see in the pictures, we chose precise cut angles that we hoped would help to develop the strongest arch possible and best distribute the load. Our prototype construction and testing went well. As you can see on the right, the pieces didn't always align perfectly because of our holes not aligning well when we drilled them, but we came up with a plan to fix that and improve the stability of the bridge. And when we balanced the weight on the top of our bridge, it was very strong, so we knew that the overall design was effective. As far as improvements on the prototype and the final build, we decided to reconstruct our bridge with changed cut angles to improve the strength, modified piece lengths so that we could change the distribution of weight, and then we used metal rods in between each section of wood to help prevent rotation and improve the strength of the bridge, and then we chose to use one section parallel to the ground instead of 3 to prevent pivoting on the top of the bridge when weight was applied, not in the center.
So finally, we went to test our bridge at Fed. So to summarize the performance, it held all of the weight used in the tests, which was 130 pounds. We assembled the bridge in about 53 seconds, which was well under the required time of a minute 30. And the bridge weighed in at a nice low 5 pounds, much less than the required 8-pound limit. But despite being one of 4 bridges to hold all of the weight and one of 2 to do it without looking intensely stressed or flexing a lot, the bridge did not place in the overall Fed rankings. But instead of being mad about that, we just decided to test it on our own and see how much weight it could hold. So, after Fed, we decided to test the bridge and see how much weight it would hold, and what the point of failure would be, since it never gotten close to failing before. So for the test, we went to Carmichael Gym and ended up stacking 45-pound weights on the bridge. So we were able to stack 7 45 plates for a total of 315 pounds. Since our bridge weighs in at slightly under 5 pounds, it held over 63 times its own weight.
So if we had to do this whole thing again, what would we do differently? Well, just kind of reviewing over everything that we've already talked about is our bridge held the max weight. It held more than it was supposed to be able to. So we were really good in that regard. But whenever we did test the max weight, we saw that the screws at the bottom fell out and the bottom twisted out. So one thing we would do differently is we would add longer screws and just make a sturdier foundation so that it could hold more weight. The actual integrity of our bridge did not break. It was just that the bottom twisted out. So we would change that. We would also probably try to be a little more creative. We looked at all the other designs that all the other people had, and while ours performed really well, it may not have been the most aesthetically pleasing. So we would definitely make a more creative bridge, or creative looking bridge. So more changes for next time is we would definitely add a suspension point. When we got to Fed, we thought they would test it by compressing it from the top, but they actually just ended up tying a string around it and hanging weights from that. This was not how we designed our bridge to be tested, so yeah, I would just say for future Fed students, make sure you prepare for it to be tested both ways. And again, we would try to make our design a little more enticing. Advice for future Fed students, as I said, try to be a little bit more creative. The job is not just designing a functional bridge, it's also making a good looking bridge. But one thing too is I would definitely pick a design that played to your strengths. Like pick a project that you're good at. Well, E101 teaches you the design cycle and it teaches you how to properly prepare for a project. It will not teach you how to complete your specific project. So pick a project that you're at least familiar with, that way you kind of know what you're doing while you're doing it. Also, make a timeline and stick to it. With us, we found that it was really easy. Once we picked our dates and everything, we had a lot of time. We had a lot of time to build multiple prototypes, and this really worked out well for us. Yeah, and if you want to win, just aim for not just functional but also creative. I think we failed in this area. Our bridge was not as enticing as it could have been.